So orbitals are specified with a number and a letter. The numbers are 1, 2, 3, just like Bohr's orbits. That number is called the principal quantum number. As the principal quantum number gets larger, the energy increases. So, if n is 4, that's a higher energy orbital than n equals 1. The letter indicates sort of a sublevel or a subshell, and that gives us the shape of the orbital. And these letters are not A, B, C, D, as you might expect. S, P, D, and F, there's historical reasons that those letters ended up being used. So let's look at the lowest energy orbital. So if we have a three-dimensional grid here, and these are dot representations of where the electron is. So you could imagine taking a multiple exposure photograph, where you take a picture, and then 30 seconds later, you take another picture, and every time you take the picture, every time you open the shutter, the electron is somewhere else. If you take enough pictures over a period of time, you're going to see that most of the time the electron is around in here. And towards the outside of this, less frequently, and we're not really seeing the electron out here much at all. You have the idea of what this weird picture is? So the dot density represents the probability of finding an electron. We can also represent it as a geometric shape, because drawing all those little tiny dots is really, really tedious, and we don't want to do that to represent the orbitals all the time. So overall, that shape was spherical. So we can represent this as a sphere. The sphere is not like a plastic container that contains the electron's bouncing around inside of it. That's not what it is. It's just a representation of this dot picture. We see that it's spherical, and a sphere is easier to draw. So that is a volume within which the electron is found 90% of the time. And we do expect the electron to be outside of that 10% of the time. Debating whether to tell the story or not. I'll tell you the story because I just like this story. So I have 6 children. My youngest is 9 now, and he's a lot easier to deal with. But when he was like 2, he was quite the escape artist. And he's a critter. So if you imagine maybe, looking at an overall picture of the house and saying, okay, where's Andrew? That's the little guy. Where's Andrew? Let's see, how big is that? Well, at any given time, so maybe Andrew's over there. And another time you find him over here. And then, 10 minutes later, where's Andrew? Oh, he's over here. And, so you do that throughout the course of the day, and you see that there are some patterns to his behavior. Can you guess the TV's over here? So, you'll find him near the TV more often, but you'll also find him in other places, and sometimes in the backyard. And then one time when he was 2, he got out, took the neighbor's big wheel from across the street, and rode 3 blocks towards his uncle's house. So there's Andrew over there. What the heck, right? 2-year-olds aren't supposed to do things like that, but Andrew is a lot like an electron, very squirrely and unpredictable. So this is the sort of idea that we have for these orbitals. It's like, okay, where is Andrew? Well, probably 90% of the time he's on the property, but another 10% of the time, I could tell you stories all day about strangers bringing him back from odd places. He has 2 guardian angels, I'm convinced. Don't report me, please. He's not being abused or neglected. But you get the idea? So the electrons are probably within that shape, but you don't know exactly where. You don't know if they're moving or sitting still or exactly what they're doing, and they might be outside the shape. But the orbital is a probability, a region of probability. Probably the electron is here. Any questions? So here we have the solid shape superimposed on that dot representation. So if the solid shape is 90%, then we do expect 10% of the time that the electron is going to be outside of that. This is an s orbital. So the s orbital is spherical, so that's kind of nice, s and spherical. So if we look at a hydrogen atom that is undisturbed, meaning we're not like zapping it with electricity or something, the one electron that it has is going to be in the lowest energy orbital that it can be in, and that's going to be the 1s orbital. That's called the ground state for that atom. All of its electrons are in the lowest, the most relaxed state. It's just chilling. Okay. Electrons, much like little boys, actually this part refers better to teenage boys. I have a couple of those as well. Teenage boys will get up and they will do stuff, right? They'll like go play paintball, or they'll go to the gym, or they'll go to football practice, and they'll do all this energetic stuff, and then they come home, and what do? They either lay in their bed with their phone, or they lay on the couch and watch TV, right? So it's like what? Low energy. That's the ground state for electrons. They can go up and do stuff, they can get excited, they always come back to the ground state. Okay, the lowest energy state. The absorption of energy causes the electron to jump to a higher energy orbital. That's the kid gets excited and goes out and does something, right? That's the excited state. The excited state is unstable. It's not sustainable. You can't sustain that activity indefinitely. You have to come back and relax in between. So all atoms have one ground state where everything is as low as it can be in energy. And there are multiple excited states. You could be a little bit excited. You could be tremendously excited. There's lots of different possibilities. Any questions? So the first energy level is called the n equals 1 principal shell. That only has one subshell, the s subshell. So here we have the 1s orbital. Now, in that second level of energy, there is also an s orbital, the 2s orbital. So this is another region of space in which you can find an electron, but the electron in this region would have higher energy than in the 1s. So this one is higher in energy, and it's going to be slightly larger than the 1s. In that second level, there are two different types of orbitals. There's the s orbital, and then there's a p type orbital. The p subshell has 3 different orbitals in it, and those have different shapes. So it's kind of like 2 balloons or a dumbbell, 2 drumsticks. Use your imagination. So in this orbital, the electron can be over here or over here. This has the same shape, but it's oriented differently in space, and this one's vertical. So they're all the same shape, but they're arranged differently, and they don't really overlap with each other. You're probably thinking this is like not making a lot of sense. This is a very difficult topic to understand. It's a difficult topic to teach too, because I'm like, I hate that I have to tell you about this. It's very cool once you understand it, but until then, ugh. Okay, we'll keep trying here. So we have these shells, and it's fine to think about the Bohr model. The Bohr model is, hopefully at this point, the Bohr model is like, ooh, I liked the Bohr model now that I'm getting into what is she talking about over here? The Bohr model with its nice little orbits, right? It's okay to think about the Bohr model and to say, well, this is like that in the Bohr model, as long as you understand that the Bohr model is not the end-all, be-all. So n equals 1, 2, 3, 4. Those are like the increasing sized orbits in the Bohr model. But now we have subshells. And the number of subshells corresponds to the number of the shell. So the first level has 1 sublevel. The second level has 2, the third has 3, the fourth has 4. So in the first level, you only have the s orbitals. That's the spherical one. On the second level, you have the s orbital, and then you also have a subshell that has the p orbitals. You go up to the third level, there's s and p, and then there's another one, the d. Those shapes are even stranger. And the fourth, there's s, p, d, and f. Let me just, do I get to this? Okay. I'm going to jump ahead to this. So I have an analogy. If you haven't noticed, I really enjoy analogies. So this is my analogy for quantum mechanics. I call it the quantum hotel, a discount resort for electrons in Mrs. K's chemistry land. Okay, so imagine this hotel. It's kind of a strangely shaped hotel because it's smaller at the bottom and gets bigger at the top. But the first floor only has 1 room on it. And it's not like room 1, it's called room 1S. It's an S room. The second floor has 2 rooms, an S-type room and a P-type room. The third floor has 3 rooms, S, P, and D. And the fourth one has S, P, D, and F. These different types of rooms, just like if you go to a hotel, you might get a queen room where it's got 1 queen bed, or you could have 2 king beds, or there's different configurations, right? So here the S rooms have 1 bed, the P rooms have 3 beds, the D rooms have 5 beds, the F rooms have 7 beds. It is a strange hotel, right? And these are just double beds, and they only allow 2 people to sleep in a bed, okay? So 2 people in a bed. So if you have this D room, and it's got 5 beds, how many people could you possibly sleep in there? 10, 2 in each bed. They're really, really strict about not sleeping on the floor. So the correlation between my quantum hotel and the quantum mechanical model is that the floor of the hotel is like the principal shell, 1, 2, 3, 4. These rooms are like the subshells in the quantum mechanical model. Each bed is like an orbital. People in the hotel are like electrons in the quantum mechanical model. And money is like energy. So now that I've kind of introduced you to that idea, we're going to go back and be able to use those terms when we talk about this stuff. So here's the first floor. There's only the 1 room, S room. On the second floor, there's 2 rooms. Third floor has 3 rooms. Fourth floor has 4 rooms. Okay? This F room has 7 beds. The D room has 5 beds. The P room has 3 beds. The S has 1 bed. Why? Because. So the third level, the third floor, the third principal shell, 3 sublevels, 3 rooms, S, P, and D. The S and the P subshells, rooms, have 3s and 3p orbitals, those beds. They're similar in shape. The orbitals are slightly larger, and they're higher in energy. It costs more money to stay in those beds that are higher in the motel, because it's a higher energy. And the D sublevel has 5 D orbitals. So the D room has 5 beds. These are the shapes of the orbitals. I don't expect you to remember those. They're very strange. So an electron configuration shows what orbitals are occupied by electrons for a particular atom. And this is like the hotel clerk at the front desk. He needs to keep track of what rooms are occupied, right? And so he's got, modern hotels, you've got this computer that tells you. Well, he's got this weird little tally sheet where he keeps track of which rooms have how many people in them. And so we call that an electron configuration. If we look at the ground state hydrogen atom, so the hydrogen atom in its lowest energy state, it's not excited at all. Hydrogen atoms have one electron. That one electron is going to be in the lowest energy orbital. So that's going to be in the n equals 1, n equals 1 principal level. And there's only one orbital there, so it's going to be in that orbital, the s orbital. So 1s, that is the lowest orbital, lowest energy orbital. And then we have a superscript 1 to say there's one electron in there. So this is like the first floor S room, and there's one person staying there. We can also draw orbital diagrams, which is more like a picture, and I really like the orbital diagrams. So for hydrogen, this box represents the 1s orbital, and the arrow represents one electron. And this is a lot like a bed in the room, and there's a person sleeping in the bed. The direction of the arrow represents electron spin. Electrons can have positive or negative spin. You could think of it a little bit like a Beyblade top. Some of them spin counterclockwise and some of them spin clockwise. Right? They both spin, but they spin in different directions. The Pauli exclusion principle tells us that the orbitals can hold no more than 2 electrons with opposing spins. And so we symbolize that as 2 arrows but pointing in different directions. So in the hotel, they have a rule that you can only have 2 people sleeping in a bed, and they have to have opposite spins. So what does that mean? So here's a bed. Well, what am I doing here? So here's the bed, right? So this is the head of the bed, and this is the foot of the bed. So in analogies, things get a little strange. So all of the electrons are male. Not sure why, but all the electrons are male. And so here's this room, and it has one bed in it, and the first electron comes in. He's like, oh, I'm tired, I'm going to get into bed. And so this part of the arrow, that's his head. The head of the arrow is the head of the electron. So he's going to sleep right side up in the bed. Another electron comes in, and he has to sleep in this bed with this other electron. Do guys generally like doing that? You ever been on a trip, like a school trip, where there's a bunch of guys and there's 4 guys and there's 2 beds? And usually they're not going to share the bed, right? They'll like arm wrestle or something to see who gets the bed and the other people sleep on the floor, right? That's what always happened when I was in school. The girls are like, yeah, we'll share. No, just stay on your side. Guys tend not to do that. So what do? There's a rule, and they come and inspect. You can't sleep on the floor. You got to sleep in the bed. So what they're going to do is they're going to sleep upside down in the bed. We are going to avoid appearances of any monkey business. We are just sleeping here, right? Being very proper. So they're going to sleep upside down. Does that make any sense at all? This means yes. This means no. Okay, I got at least a couple nods. So spin up and spin down. Scientifically, the electrons can be in the same orbit only if their spins are paired. If they're the same spin, they're going to repel each other and they won't be able to stay in the same orbit. The business of the sleeping head to toe in the bed is just to help you remember how things go. Okay? So let's write electron configurations and orbital diagrams for helium and lithium. I'm going to do the orbital diagrams first because I think they're easier. So how do we do this? Well, let's do helium. We need to know how many electrons does helium have. So we look at the periodic table, and what's the blue number above the symbol for helium? 2. That's how many electrons it has. It's also how many protons. So helium has 2 electrons. So we think about this hotel, and electrons are cheap. It's a discount hotel, right? They're going here because they want to save money. They're not going to hang out here a lot. They're going to go off and do other things. So they come into the hotel, they want the cheapest room, they want the lowest energy orbital. That's on the first floor, and there's only one room there, it's the S room. So here we have the 1s orbital. So the first electron comes in, he's like, oh, I'm bushed, I'm going to go to bed. He sleeps head up in the bed, right side up. Helium has 2 electrons. The next electron comes in. These guys are really cheap. Could he spend more money and go up to another room and have his own bed? He could, but he's cheap. So he's going to sleep in this bed, but he's going to sleep upside down. Okay? That is the orbital diagram for helium. The electron configuration just uses letters and numbers, not pictures, and so it's much easier to type out. So the electron configuration is like what the guy at the front desk might have, and he's got an indication that in the 1s room, I have 2 electrons. So 1s, 2. That's the electron configuration for helium. So let's do lithium. How many electrons does lithium have? 3. It's element number 3. 3 electrons. So imagine 3 electrons coming into the hotel. So here's the first room, the 1s room. That's the cheapest. First electron sleeps right side up in the bed. Second electron bunks in with him but sleeps upside down. Third electron, you can only have 2 people per bed. You can't stay in that room. He's going to have to go to the next room on the next floor, right? So on the second floor, there's an S room with 1 bed in it. And so he's going to go up there and sleep in that bed. So then the electron configuration, we're going to say, well, in the 1s subshell, we have 2 electrons. And in the 2s, I have 1 electron. So 1s, 2, 2s, 1. It sounds like some weird code or something. Any questions? The reason that the Bohr model didn't work for anything but hydrogen is because when you get more than 1 electron, the electrons interact with each other and make things go very wonky. And the Bohr model just didn't have enough parameters to be able to deal with that. So here's here is a diagram showing energy going up and showing the different subshells and how their energies are relative to each other. So the 1s sublevel is the lowest in energy, and the 2s is next highest in energy. And then the 2p is higher in energy than that, just a little bit. So in the hotel, the S room on the first floor is the cheapest. The S room on the second floor is the next cheapest. The P room on the second floor costs a little bit more. So, come up for a reason, I'd rather sleep in the smaller room. Well, maybe this one is by the elevators in the ice machine, and so it's not as desirable as this one, which is quieter. Or maybe it has a better view or something. I don't know. But it is what it is. So these are more expensive rooms. You go up to the 3rd floor, and the S room is the cheapest. The P room is a little more expensive. The D room is more expensive. But a weird thing has happened. The S room on the 4th floor is cheaper than the D room on the 3rd floor. How the heck does that happen? Well, maybe they're running a special or there's some Groupon deal or something, but it's how it is. So going up in energy, it's 3s, 3p, the next one is 4s, and then 3d. And then we go to 4p, and 5s, and 4d. Is that confusing or what? That's confusing. I'm going to show you how all that information is hiding on the periodic table. So let's write the electron configuration and orbital diagram for carbon. How many electrons does carbon have? 6. 6 electrons. So let's draw some rooms here before we put the electrons in there. So the first room is going to be on the first floor, the 1s, and then we've got the 2s, and also on the second floor, there's a P room. The P room has 3 beds, but they're all in one room. So we represent that as 3 boxes, but they're stuck together. So that's the 2P sub-level, or the P room on the second floor of the hotel, and there's 3 beds in there. So we could put up to 6 electrons in there. Carbon has 6 electrons. So we're going to put them in the cheapest rooms first, and then as necessary go to more expensive rooms. So the first electron comes in, he gets to sleep right side up in the bed. The second electron is also going to stay in that room, but he's going to sleep upside down. Third electron has to go into the 2s room. He claims right side up in the bed. The next electron goes in there as well, but it's going to sleep upside down. Now, the 5th electron has to go up into the 2p room, and so he's just going to grab the bed that's closest to the door. Now, electron number 6 comes in. If you were a person staying in this weird hotel, and you were coming into this room, would you sleep upside down with this guy you don't know, or would you take your own bed and sleep right side up? You take your own bed, of course. And that's what the electron does. It take its own bed and sleep right side up. So that's an illustration of Hund's rule. When we're filling orbitals of equal energy, electrons fill them singly first with parallel spins. So here we have 3 orbitals that are the same energy. We have 3 beds in the same room. You're going to pay the same amount of money regardless of which bed you sleep in, right? So the electrons are going to take their own orbitals if they can. Now the electron configuration for that, in the 1s, there are 2 electrons. In the 2s, how many electrons? 2. And in 2p, how many electrons? 2. The electron configuration doesn't give us as much information as the orbital diagram does. This doesn't tell us that those electrons are sleeping in separate beds, that they're in separate orbitals. It just tells us that in this 2p level, there are 2 electrons. Any questions?
How do you know 2p has 3 rooms?
How do you know that 2p has 3 rooms? Because I told you so. It has to do with the quantum numbers, and so it's not that we made this up. A lot of really, really crazy math and modeling, and they found that this is what fit with things that were observed. And there's a pattern here. No, this one. So all of the s orbitals just have, the s subshells have 1, and the p is 3, and this is 5. And the next one, F, is 7. 1, 3, 5, 7. They are odd numbers. 1, 3, 5, 7. It's a good question. Okay, so there's that. Yeah. This isn't a one way to do orbital filling to figure out what the order is. If you like that, go ahead and use it. I'm not going to talk about it in class because it's also on the periodic table. So the periodic table has all of this information kind of hiding in it. So these first 2 columns that stick up, there's 2 of them. The s orbital, the s subshell, can hold 2 electrons. Over here, helium and hydrogen are like the baby brothers of the element family, and they just don't always obey the rules. Right? They get away with stuff. So forget about him. He really should be over here, but he's being naughty and he's hanging out over there. Here we've got 6 columns. The P room has 3 beds. It can hold 6 people. The p subshell has 3 orbitals. It can hold 6 electrons. There are 6 columns here. The D sublevel has 5 orbitals. The D room has 5 beds. It can hold 10 electrons, 10 people. If you count across here, there's 10 columns. The F block, 7 beds, 7 orbitals, 14 electrons. If you count across here, 14 columns. I find that wonderful and creepy at the same time. This periodic table and how it was arranged was made before we knew what electrons were, just by observing patterns in the properties of the elements. And then we find out independently that there's this other quantum information hiding in there. It's really mind-boggling. So periods in the periodic table are the rows, 1, 2, 3, 4, 5, 6, 7. So you can kind of use this like, it's a little bit like playing Battleship. You know, you say C5, direct hit. C6, you sink my battleship. You can find an element that you're trying to do an electron configuration for, and you can read its last electron off the periodic table. So if we're going to look at silicon, so silicon's over here, it's in row 3, and over here, it's in the P block, right? And we count 1, 2. So this ends with 3p2. You can imagine this as adding electrons. So here we've got hydrogen. That 1 electron is going to go into that lowest energy orbital. And then helium is adding 1 more. So that's also going to go into that 1s orbital. When we get up to lithium, we're adding another electron. It has to go into the second floor, the second level, and it's going to be in the s orbital. Beryllium adds 1 more. So now we've got S2. We go to boron. Now that the next electron, the 2s room is full, it's going to have to go up to the 2p room. So this is 2p1. Carbon is 2p2. 3, 4, 5, 6. Now we've filled up the p room. So the next electron that comes in has to go to the 3s room. And then we'll fill up the 3s room, and then it'll go to 3p, and we'll fill up that one. And then we'll go to 4s. And up till then, everything's all nice. And then things get a little weird. Because we saw this business, right? 3p, 4s. What happened to the 3d? Well, these are the 3d. So this is the D block, but it's in the 4th period instead of the 3rd period. The way I think about this is that part of the periodic table sunk, kind of like the valley floor is sinking as the water table drops, that it was supposed to be up here, but it has sunk down. So this is the D block, but these Ds are not 4D. If we say that this is n equals 1, n equals 2, these are going to be n, oops, what did I do? No, I don't know what I did. So n equals 3, n equals 4. So in that D block, it's n minus 1. It's not n minus 1, n minus 1, because it's sunk. So this looks like it should be 4D, but it's 3D. 3D, and then this would be 4P, and 5S, and now that sank again. This is 4D, and 5P, and 6S. And then we get some other wackiness where these are sunken. I'm not going to make you do any of those on an exam. So in summary, lower energy orbitals fill before higher ones. Orbitals can hold no more than 2 electrons, And if there are two electrons, they have to have opposite spins. If you have orbitals with the same energy, they're going to be occupied singly first with parallel spins. So the cheap rooms fill up first. You can't have more than two people in a bed. If they do sleep in the same bed, they sleep head to toe. And if you've got multiple beds in a room, people are going to take their own bed and they're going to sleep right side up if they can. Okay, electron configurations and orbital diagrams for nitrogen, oxygen, fluorine, and neon. Okay, well, I'll start with nitrogen. How many electrons does nitrogen have? It's got 7. So I'm going to draw some rooms here. So here's the 1s room and the 2s room. The 2p room has 3 beds. And then there's the 3s room. And then there would be the 3p room. If there's nobody staying in a hotel room, does the hotel room still exist? Yeah, it's still there. It's just waiting. These orbitals exist whether they have electrons in them or not. So an electron could always get some energy and move up. It's a little bit like, maybe the electrons were out gambling and they won some money, and so they come back to the hotel and they're like, I want to stay in the penthouse tonight, right? So they go up there and they have a great party and everything, but they don't have enough money to stay up there indefinitely, so eventually they're going to have to come back down to the cheap room. Okay, so nitrogen has 5 electrons. So let's put the electrons to bed. So 1, 2, 3, 4, 5. Where's the next one going to sleep? In his own bed, right? 6, 7. So that's nitrogen. So the electron configuration would be 1s2, 2s2, 2p what? 3. These superscripts, 2 plus 2 plus 3 equals 7. Those should add up to the number of electrons. So that's nitrogen. How about oxygen? How many electrons does oxygen have? 8. It's got 1 more. So we could just take this diagram for nitrogen and add 1 more electron. Where's it going to go? It's going to go head down in the 2p. You'll just grab the one closest to the door because it's easier. And then to change the electron configuration, all we have to do is change the number on the 2p. Now we got 2p4. Let's do fluorine. Fluorine has 1 more electron than oxygen. Where's that electron going to go? It'll go right here. It's going to be right in there. And then the electron configuration, whoops, be 2p5. Look at fluorine on the periodic table. It's in the 2nd row, and it's over in the p block. And if you start at the beginning of the p block with boron and count 1, 2, 3, 4, 5, 2p5. How about neon? Well, we're just adding another electron, right? That electron's going to go in here. So now in the hotel, the first 2 floors are completely full. There's nobody on the 3rd floor, and there's no more space available on the 2nd floor. It's the complete filling of the n equals 2 principal shell. You can imagine that when you get down to things like strontium with 38 electrons, it could get a little tedious, right? 1s2, 2s2, 2p3. So we do have some shorthand notations, and so what we can do is we can use the previous noble gas. So we just looked at what neon was, right? Neon has 10 electrons, and it has this electron configuration. So we could look at something that comes after neon, like sodium, and say, well, sodium is neon plus this other thing. So for sodium, the electron configuration for sodium would be 1s2, 2s2, 2p6, 3s1. And we can shorten that by saying, well, this part is the same as neon, right? So we can say, well, the electron configuration of neon, we indicate that by putting brackets around it, and then write the stuff that comes after that, 3s1. You only use the noble gases. You can't say that magnesium is sodium and this one extra thing. It's always the noble gases. Sometimes called the noble gas shorthand. Write electron configurations for each element. Okay, so let's do this off the periodic table. Do I have a periodic table here? No. There's one on the wall. So we look at aluminum, fine aluminum on the periodic table. What row is it in? It's in row 3, right? And what block? S, P, D, or F? It's in the P block, right? Where there's the six columns over there. And it's the first one in that block. So its electron configuration ends with 3p1, just from its position in the periodic table. And so I can look at the rest of the periodic table and see, well, that first row, think of helium as being over there where it belongs next to hydrogen. So 1s2, there's 2 electrons there, 1s2. And then we go to the next row, 2, and then we've got that s block, and there's 2 squares there, 2s2. And then we come across boron through neon. There's 6 electrons that we're adding there, adding those to the 2p level, 2p6. Then we come down to the 3rd level, and there's sodium and magnesium. Those are in the S block, 3s, and we filled those, 3s2. And then the next one is aluminum. That's in the 3p block, and it's the first one. Yes?
Would it be the same if we did the same as you did with neon?
Yeah, we can do you mean the shorthand version? Yes. So this part here is neon. And so we can also write electron configuration of neon, and then let's just look at what comes after. And it's 3s2, 3p1. Yeah, it can't be magnesium. It could be like krypton, any of the noble gases. And you want to use the next smallest of whatever element you're doing. This is one of those skills, I guess you could call it, that I can help you best with one-on-one. So this is going to be confusing. So ask me questions and we'll get it straightened out. Once the light bulb clicks on, it's really pretty simple. Until then, it's just this weird mess of numbers and letters. Let's do strontium. Let's skip bromine because we're running out of time here. So strontium, let's just do the noble gas shorthand version. So I see that strontium is in period 5 of the periodic table. So I'm going to go up to period 4, the next one up, and go all the way to the end and find the noble gas. So that's krypton, right? So strontium is going to have the same electron configuration as krypton plus a few extra electrons. So strontium is on period 5, and it's 2 blocks over. It's the S block there, so it's S2, so 5s2. You're going to have lots of questions about that. Let's do an orbital diagram for argon. So argon, how many electrons? 18. For orbital diagrams, I think it's best to draw the boxes first and then stick the electrons in. So 1s, 2s, 2p, and after that comes 3s, and 3p, and next would come 4s, and after that would be 3d. I know I'm drawing more than we need. So now we're going to put the electrons in, and we're just going to count as we go along. 1, 2, 3, 4, 5, 6. They'd like to sleep in their own bed if they can. So that was 6. 7. Now we got to pair up 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And that matches up with where argon is on the periodic table. It's in the 3rd row at the very end of the p block. So its electron configuration ends with 3p6. And there we've got the 3p6.